Okay. So let's look at first the imine hydrolysis. All right, first it's good to be able to identify what the imine functional group is before you do any reaction to it. All right, so these atoms are going to be part of the imine functional group. All right, and when we think about breaking this apart, so when we hydrolyze this, these are going to be our two products. Okay. And you can see that we're making from this imine, when we hydrolyze it, a ketone and a primary amine. Right? So those are the two functional groups that when we mix them together, right, that's what makes the imine. So this is just the reverse reaction of the imine formation. Okay, so if you're trying to break this down, right, you want to focus on the imine and realize that it's always going to break down or be hydrolyzed in the same way. Right, so when we look at the starting material, you can see that the nitrogen or the carbon that has a double bond to the nitrogen will become the carbonyl. Right? And the oxygen that we're adding in water just like when we hydrolyze an acetal or ketal, that oxygen in the water becomes the carbonyl oxygen. Right? On the other side of the nitrogen in the imine, right, the other carbon attached to it, that's going to become the aminocarbon of the product. Okay, in terms of everything, every other atom on this structure, right, you can see that every other atom is remaining unchanged, right? These 5 carbons in the ring remain 5 carbons in the ring. Right? Nothing is happening to them chemically. No arrows should be drawn to those carbons, right? You can see all of the carbons on the right-hand side of the nitrogen. All of those carbons and hydrogens on the right-hand side of the nitrogen are still there. Right? So mechanistically, the only thing that's happening is happening to the nitrogen of the imine, the carbon of the imine, the oxygen of water, and the hydrogens of water. Right? Those are the only 4 atoms that you should be drawing arrows from or arrows to in the mechanism. Right, so let's draw the mechanism out. Okay, so whenever we mix water and sulfuric acid, that's going to react really, really quickly and produce the hydronium sulfonate. Right? So even though we're putting sulfuric acid in there, right, that sulfuric reacts with water, and so this is probably the acid that's available to us in the reaction. Right? So we'll take that acid, and we'll use that acid to protonate nitrogen. Right? I'm going to abbreviate this phenyl group's pH so we don't have to draw it out every time. And then nitrogen gave away a pair of electrons, so it gets a formal positive charge. Right? If you look at what we just did here, this is similar to the first step of ketal formation, right? Where we take a carbonyl and we protonate it to produce a really reactive carbonyl. Right? So what we're doing here is we're taking an imine, right? That bond, carbon-nitrogen bond is polarized towards the nitrogen. We're protonating that nitrogen to make this carbon-nitrogen bond even more polarized, right? So that makes this carbon a good electrophile now. So the water that we have in the reaction can add to the carbonyl, or the aminocarbon. Right, and we arrive at this intermediate. Right, so this carbon-oxygen bond, that's the sigma bond that was just made. And so that's the first bond. If we're trying to replace this nitrogen with an oxygen to form a carbonyl, that's the first carbon-oxygen bond we're making. Okay, so we're starting to kick the nitrogen group off. Right, if you look at where we are and where we need to go, we need to release the amine. We also need to add another hydrogen to that nitrogen in order to do it. Right, and so we're going to take protons off of the oxygen, right, put that proton on the amine, and then we can kick it off as a leaving group. We can't do that intramolecularly, 1, 2, 3, 4, right? The transition cycle is too small. So we need another molecule to act as a base, pluck the proton off, and deliver it to the nitrogen. Right? So water is in the reaction. Remember, you can't suggest something that's not in the reaction. Okay? In this case, water is in the reaction, so we can use it as a base. So once we form our hydronium conjugate acid, the nitrogen can pluck the proton from there. And that gives us our amino leaving group. Questions so far?
So when you're suggesting the products without making the mechanism, how do you know it's going to be a ketone versus an aldehyde?
So when you look at the imine, right, if this is the carbonyl that is going to form, or if we're making this imine, right, that's where the carbonyl originally was. We're hydrolyzing it, that's where it's going to form. Right? On either side of that double bond, we have 2 carbons. Just like a ketone would have 2 carbons on either side. Right? If this was an aldehyde, or if this was going to become an aldehyde, we would have a carbon on one side and a hydrogen on the other. Right? Other questions? Okay. Right, so think about what we're doing again, right? We have a nitrogen, we're trying to kick that off as an amino group, replace it with an oxygen, right, in the form of water. And so we're adding the oxygen, and then we're transferring the protons from that oxygen to the nitrogen so we can kick it off as a positively charged leaving group. Right, so that's where we are here. Just like all other groups that leave in these reactions, they don't leave on their own, right, but they're kicked off by a next door heteroatom. So the oxygen electrons will fall down, form a pi bond. Carbonyl oxygen is still protonated. And then we have our amine. And then we can use a molecule of water at the end proton off of the carbonyl oxygen. Right, and that gives us our amine product and our carbonyl product. Questions about this?
Is there only one mechanism arrow in that one?
Pardon?
There's just one mechanism arrow in that one.
Here.
Second.
Thank you. Other questions? Yeah. All right, so these are going to be the two possible enamine products that we can make, and we'll go over the mechanism for the formation of these enamines. All right, that you can see that the difference is where it comes in the position of the double bond. Right, in some of these, the double bond is on carbon 2 and 3. In other molecules or other products, the double bond would be on carbon 1 and 2. Right, again, I just want to point out why this is called an enamine. Right? Just because we have an alkene that's directly attached to an amine function. Okay, so let's take a look at the mechanism, see how both of these enamines can be formed. All right, so we're given, remember the enamine, we're starting with an aldehyde or a ketone. Right, hopefully by now you realize that aldehydes and ketones, they react in almost exactly the same way. Right? Maybe slightly different level of reactivity, but in terms of how nucleophiles attach to them, right? How we draw mechanisms of addition to ketones and aldehydes, more or less the same functional group. Right? And then for enamines, we have to add a secondary amine. Right? So an amine with only one hydrogen and then 2 bonds to carbon. Amines, remember, that's a primary amine. Enamines, it's a secondary amine. Right, and then this is going to be acid catalyzed. So we'll start the mechanism by showing the addition of the amine group to the carbonyl. Remember, amines are nucleophilic enough to add to carbonyls without forming a more reactive electrophile, right? Without protonating the carbonyl first. All right, I'm going to just show sulfuric acid as the acid we're using in this reaction. Okay. Of note, there is no water in this reaction, right? So we can't suggest water as a acid or base in this reaction. Right, but the little acid we do have is going to protonate the oxygen. and then we're going to do a two-step proton transfer, right? And I'm just going to abbreviate it today, right? But on exams, on homework, you should, for the time being, plan to show both steps of that proton transfer. Okay, so what I did was I took the proton off of the nitrogen and I added it to the oxygen. Right? What molecule in this reaction is going to be capable of helping with that proton transfer? Okay.
Amine.
Great, yeah, so we could take the molecule of the amine, really good base, and that can pluck this proton off and then deliver it to the oxygen. Anything else? So I would say Frank gave the answer for the most probable molecule, but is there any other thing? Yeah, Joe?
I used the ketone.
Great, yeah, so the carbonyl oxygen, right, not super basic, but if it's nearby, there may be enough of it protonated that it can serve as a shuttle as well, right? So not the most probable, but still possible, right? We can write that in our mechanism as well. All right, so once we've protonated that oxygen, you can see that we've formed our water leaving group. So we can kick that out through elimination, right? Same way we do all leaving group, or the same way we eliminate all leaving groups, right? The atom from next door forms a pi bond, and we kick out our leaving group. Loss of water takes us to something called the iminium intermediate, right? So this is just a positively charged imine. Right, and then from here we have two options. Let's show this here. Okay, first option is to take the amine, pull a proton from carbon 1, and you can see how those electrons can flow up then to the positively charged nitrogen. Right? So this nitrogen is getting a new proton, right? So we're regenerating that acid. Okay, these sigma electrons form a new carbon-carbon pi bond, and then the old pi electrons get shuttled to nitrogen to satisfy the charge. So that's one option, right? To get the other product, we choose to pull a proton from the other side of the amine. Right, so we take our same amine, right, just showing a different proton pull. That's going to get us our questions about this?
So, up by the two first step proton transfer.
Yes.
We got rid of the hydrogen while we just added it to the oxygen.
Yep, yeah, so I didn't draw this out, right? But the way that we would show this two-step transfer mechanistically is we'd take a molecule of the amine, show it pulling this proton off, right? And then the conjugate acid of that, the one with two hydrogens, will protonate the oxygen in the second step, right? So I've circled the protons just to show you that in terms of a net transformation, right? This proton is being transferred to that oxygen. Other questions? Yeah.
I may have just like missed it, but why is there suddenly a hydrogen at the end of
Here?
yeah.
It's always there, right? We're just not drawing it in. There are 3 hydrogens on that carbon,
Okay.
right? We're not using them mechanistically, so I don't draw them in until we are showing them in the mechanism.
Okay, and then
Right.
you just added another amine group to be able to do that proton transfer because they're
Well, we have the amine in the reaction at the beginning, right? So yeah, so we're just using it as a base here. Does that make sense?
yeah.
Okay, other questions? Joey, yeah.
Would it be particularly incorrect in the final mechanism to return that hydrogen to the sulfuric acid?
No. So that's a good point, right? So in this reaction, right, if we're using the sulfuric acid, we're going to generate the sulfonate anion. Right, so that's going to be carried through the whole reaction. So if we wanted to use that as a base at the end, that's fine. Again, the amine will be the stronger base, more probable base.
And the reason why you don't use the acid catalyst in the first step is because the nitrogen is very nucleophilic, so you don't need it.
Great, yeah. So amines are way more nucleophilic than alcohols, right? So alcohols, because they're relatively poor nucleophiles, we need to, we show the protonation of the carbonyl first, right? Because that's going to be a fast enough reaction. With amines, because they're less electronegative than oxygen, than nitrogen, right? Their electrons are a little more promiscuous, held out, right? We're not as careful with those electrons, so it's a much more nucleophilic atom, right? So we don't need to protonate this oxygen first. Allison?
For the water leaving group, could you use that deprotonated acid as a shuttle or no?
Sure, yeah. If you wanted to show this with the sulfonate anion, you could show the sulfonate anion transferring that proton.
For the water leaving group, since you have it broken off, wouldn't that then be also a product of the reaction?
Sure, yeah. So we could show that as a product of the reaction. I mean, typically, we're not trying to make water in the lab. So we usually consider it a byproduct of the reaction, right? So it is a product, but not something we typically care about.
Okay. So you don't have to necessarily show it as a product.
So, we've seen a couple of different types of schemes. If you're showing the equilibrium reaction, where you're showing all of the starting materials on one side and all the products on the other side, then yes. Yeah. But if you're just showing a reaction scheme where you have the product that we're paying attention to, reagents around an arrow and conditions, and then, the starting material we're paying attention to, reagents and conditions around an arrow, and then a product, then yeah, you don't need to show it.
How do you know at what point to stop? Like, just keep, to stop doing the mechanism, instead of just keep, adding more acid and going further, I guess. Because there's so many steps, I don't.
Right, I mean, so that's why when we talk about these, we talk about them in terms of the functional groups that are reacting, right, and the functional groups that we're making, or the group that we're making. So in this reaction, if we know that we're making an enamine, then we've got to stop at the enamine, right? I mean, in reality, if we keep this in acid, this nitrogen is going to get protonated, things are going to start going back and forth, but we're just trying to rationalize, right, if we're starting with these two, what product are we going to make? Okay, and so if as long as you're learning these by functional group, then yeah, you should know where to stop. Okay.
Is it right that if the reactant is ketone, then we will make two products and if it's aldehyde?
Yeah, excellent. So that's a really good point. Right. So if this is a ketone, and we have a carbon with a proton on either side, right, that can be protonated, then we're going to form two products. Started with something like this, then we could only form one product. Because there's only one carbon of that ketone that has protons that we can pull off. Right? Here there aren't any protons on that alpha carbon. Okay? Likewise, if we start with an aldehyde, right, we can only form one product. So the fact that we're getting two products here comes from the type of ketone that we're starting with. Right, so we're starting with a ketone with two alkyl groups. And those alkyl groups each have hydrogens that can be pulled off in the last step. Questions? Yeah, Hannah.
So like for most, whenever you're using the ketones, right, you're gonna usually have two products sometimes like.
If you're forming an enamine, yeah, and you have a ketone that's, we call this being enolizable, and you have protons on either side of the carbonyl. So if a ketone is enolizable on either side, then you will get two products. Right? This is not going to be a 1-to-1 ratio. We're probably going to form more of this. There might be like 70% of that and 30% of that, right? But we're still going to form both products. Other questions? Okay, I will point out, right, when you look at this mechanism, so we're forming an enamine here, right? Obviously a different functional group from an imine, but if you look at the mechanism is almost exactly the same, right? The only difference comes at the end where on an imine we pull a proton from the nitrogen, right? For the enamine we're pulling a proton from the carbon that has sigma electrons in conjugation with nitrogen. Right? So mechanistically, they're almost exactly the same except for that last step, right? It depends what atom we're pulling the proton from. That's the only difference. Questions about this? Yeah?
The two-step proton transfer included the acid above, right? The S.
I'm not specifying. All I'm saying is that we're pulling a proton from this nitrogen, we're putting it on this oxygen. It has to happen in 2 steps, and we're using some base that's in the reaction to pluck it off, and then the conjugate acid of that base to put it on the oxygen. Right? You could use this if you want, but I'm not specifying that in this mechanism. Other questions? Okay, so let's just take inventory of the reactions that we've learned in this chapter. So we can divide them into 2 categories: addition reactions right. So the first reaction that you learned was just the hydration reaction. Okay, and this is not a reaction that we run in lab, right? This is just a reaction. We have to know that it happens because there's water almost everywhere unless we intentionally try to get rid of it, right? But anytime water is in contact with a carbonyl, whether that's an aldehyde or a ketone, right? It's going to react with that carbonyl in some equilibrium to form the hydrate, right? Whether we want it to or not, okay? This is an equilibrium, so we can't trap the hydrate, right, and expect it to stay as the hydrate because it's going to break down, right, and reestablish that equilibrium. So this is a reaction that we need to know, but it's not a reaction we go into the lab and run. It's just something that happens naturally. Okay, same thing with hemiacetal, hemiketal formation. Okay, again, right, if we take a carbonyl, an aldehyde or ketone, and we treat it with an alcohol, right, under neutral conditions, so we're not catalyzing this reaction in any way, okay, we're going to get addition of that alcohol to the carbonyl, right, whether we like to or not. Okay, so again, very similar to hydration, mechanistically almost exactly the same, right? One is using a hydroxy group attached to a hydrogen, the other is using a hydroxy group attached to a carbon, right? Water versus alcohol. Okay, the other class of reactions are going to be the substitution reactions. Right, so you can see for the addition reactions, we're starting with two starting materials, and we're ending with one product, right? So those two starting materials are combining or adding together to make one thing, right? In substitution, we're starting with two starting materials, right? And we're ending with two products. Okay, we can also group the imine formation in there. And the enamine formation. Right, so the last reaction that we're going to learn in this chapter, really quick, really easy reaction, formation of a functional group called a cyanohydrin. Right, very specific reaction. The reason why we're leaving this to the end is because this is going to be the first reaction that teaches you carbon-carbon bond formation. Okay, so in this reaction, what we're doing is we're taking aldehyde or ketone, right? Just showing a simple one here, and hydrogen cyanide. Hydrogen cyanide is a deadly gas, right? The conjugate acid of sodium cyanide or potassium cyanide, right? But it has a pretty low pKa, so it's pretty acidic for a proton on carbon. So what can happen is the oxygen of the carbonyl gets protonated by the hydrogen cyanide. Right? And then the cyanide anion, the carbon, is nucleophilic, and that's going to add to the carbonyl. Right, so that carbon-carbon bond between the cyanide and the carbonyl was formed. Right, so this is the first carbon-carbon bond forming reaction you're going to learn. Right, in terms of importance, I would say this reaction is important, but like the other addition reactions, it's something that just happens. Right, we can plan this reaction a little bit. It's part of a special class of reactions that we're not going to go over. But what you need to know is that this just kind of happens, right? Just like the other ones. Okay, 2 minutes, all right. All right, so this functional group, the cyanohydrin, is kind of a neat functional group. It's found in nature, kind of in this form. This is a molecule, general molecule called a cyanoglycoside. Did you recognize this 6-membered ring that you did the other day? Yeah. Excellent. Yeah. So this is a molecule of glucose that's attached to this, basically a cyanohydrin. And so if we treat this with acid and water, what's going to happen is that's going to form the glucose by itself. Also going to form benzaldehyde. Right, and then the third thing that that's going to form is going to be hydrogen cyanide. Right? I encourage you to work on the mechanism for this. It should be a pretty straightforward mechanism. You can see we kind of have two functional groups. We have a cyanohydrin here around this carbon. Right, but we're also going to have an acetal around this carbon, right? So if you treat it with acid and water, you have two things that you can hydrolyze, two functional groups that you can hydrolyze here. Right? This cyanoglycoside is a molecule that's found in fruit pits, like apple pits, bitter almonds, peach pits, plum pits, that kind of stuff. And whenever you eat enough of these, right, the stomach acid in our body is going to break this cyanoglycoside down into its individual components, right? So if we had a cup of apple seeds and we ate that cup of apple seeds, it would start producing a small amount of hydrogen cyanide. If we ate enough apple seeds, we'd probably die of cyanide poisoning. Right? You got to eat a lot of apple seeds. And hopefully nobody's eating cups of apple seeds. That'd be really weird. But these molecules, these types of molecules are pretty ubiquitous. There are yams that are a staple, a diet staple for people in Africa that have cyanoglycosides in them. If they don't process the yams first, then They generate hydrogen cyanide, people get sick, right? So they have to treat these yams in a very, very special way. All right, that's it. We will start with chapter 9 on Wednesday. Yeah.